Hi and welcome back to this new video about kernel memory, in which I'm going to explain some extension I wrote. Everything is open source, everything is installable by Nugget. And this kind of extension are meant to add a little bit more juice to the kernel memory library. And in this example, I wanna show you how we can implement re-ranking for a query. So we will analyze why vector search is not always the perfect solution, and where re-ranking and keyword search gives a lot of power to our search. I have already indexed with kernel memory a large number of documents inside my system, and I've indexed a lot of books I've bought with Humble Bundle about security. And I'm going to do a couple of questions. As you can see, these questions are somewhat symmetric. The first one is, can you please explain a technique called complete mediation? And the second query is the definition you can have for complete mediation, and it's the reverse query. So I know how this technique works, but I forget the name. So the answer to the first question is almost the second one, and the answer to the second one is complete mediation. Now I'm using a custom kernel memory Elasticsearch extension where I can use Elasticsearch both for as a vector search engine and both as a keyword search engine, because Elasticsearch is the best bang for your time of installation because it's free. You can install on-premise free. And you can see that I have a KM default index. It has 4,600 pieces of text. And if I'm searching all the pieces of text that contains the word complete mediation, I have only 4 segments of text that contains the keyword complete mediation. So these 4 segments are the ones I want to return from the search, because they are the only one that contains important information from all of my indexed documents. And as you can see, I have only 4,000 segments, so they are not too much, but they are enough to give vector search difficult to find the correct solution. Let's jump to the result to explain what is happening. I've posed the first question to my system. Can you please explain the technique called complete mediation? And in the second line, I specify the validation text. So what I'm doing is to perform an assessment to understand how well my RAG pipeline works. If I have a way to determine if a piece of text is good, it's a true positive, or it's not a true positive, I can give an evaluation. In this situation, the evaluation is simple, because I know that to understand if the pieces of text returned from the search is good or not good, I can simply search inside the text for the complete mediation text, because this is really simple. I'm doing a couple of questions that I know are satisfied from those 4 pieces of text. And in real scenario, you can also have a different way of validation. So maybe you have already checked all of your results and you have the list of ID that are good results. But in this situation, it's very simple. So I pose a question and I give a validation strategy, that is to check if a piece of text is good. I can simply search for complete mediation inside the text. As you can see in the second segment of this console application, the answer is correct. So the system correctly answered our question. But then it's important the analyzing the validation statistics. So I've done 2 different searches, and we will see shortly the code. So I've done keyword search. So I simply tell Elasticsearch, hey, this is the question of the user, create a standard keyword search, BM25 algorithm inside your search index. And then I've done vector search. So I've give to the Elasticsearch my vector search and say, hey, give me all the vector 10 results, each strategy. Give me the 10 vector that are much more similar to the one that user of the user question. And the important thing is BM25. In this kind of query, BM25 is perfect, because in the very first 4 results, we have all the good results. Here we have. So we retrieve 10 records, and of 10 records, the first, second, third, and fourth are the 4 records that contains complete mediation. And this is natural because BM25 is really, really good algorithm for doing keyword search. Since complete mediation is a very rare word inside the system, it is so good. And the vector search is really bad because it didn't find any good result out of my possible result. And I have, after re-ranking, we have 4 valid records out of 19 because maybe one of the record was duplicate. And the list of good record is 0, 1, 2, 3. So the keyword search places the good result in 0, 1, 2, and 4th position. So it's not perfect, but it's almost perfect. But after re-ranking, the very first 4 results are those one containing complete mediation. So it is really, really good results. In the first example, we saw that the BM25, the keyword search, is almost perfect. But then we have the other phase of the search. We are looking for the name of the technique given a description. So I've done another query this time, the second query. Can you please name the security principle that ensures blah, 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 blah. And I've, as the previous example, specified a validation string to search is always complete mediation. And as you can see in the answer stream, the security principle, blah, 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 it's the principle of complete mediation. So the system was able to answer my question this time. And this is really interesting because this time I've given the description of the technique and I asked the system to find the technique. As you can understand, this kind of question cannot be answered by keyword search. And as you can see in the validation, for standard keyword search, we have 0 valid record. Because, if the user question does not contain some keyword that are important in your system, keyword search is useless. So in this kind of query, vector search came to the rescue. Because if you look at the result, you can see that the vector search, we have 2 valid records. And the vector search is not perfect. And the good results are in position 3, so it's the 4th because it's 0-based, and in position 8, index 7. So I have a 0.5 recall because I have 4 records that contains complete mediation keyword, but I was able to find 2 of them. But the most important part is I have 10 records by keyword search, all false positive. I have 10 records by the vector search, only 2 are true positive, okay? We have 1 duplication because if you read the output, we have 2 valid records out of 19 because maybe 1 is duplicated. But after I pass to Cohere API re-ranking, the list of good record is in position 0 and 1. So as you can see, I have my cake and I eaten too because I was able to search with a keyword search. I know the keyword search is good in some scenario. Then I search also with vector search, and I know the vector search is good for other scenario. But I don't care to determine the scenario upfront. I run both of them, and I pass to the reranker. A reranker is able to take all the possible results and give the very first 2 results, the 2 that are interesting, the very true positive in the first 2 positions. So my RAG query is really, really good, and it's almost perfect. And I will give you another hint. So we look from the previous result that keyword search returned no good result and vector search returned 2 good results out of the possible 4. But this is not really true because look at the results. This is all the record in my database in Elasticsearch that contains complete mediation. The first one is a good text. The other one is completely rubbish. And that's because it is the part of book that contains the index. So it contains complete mediation, but it's garbage. And then I have another pieces of text that is maybe garbage because as you can see, it's another part of an index, okay? And I have pieces of text that is maybe more good, but the first one is probably the only good. So the idea is the vector search is really, really, really powerful technique because it was able to find correct pieces of text out from a query that does not contain anything any keyword of the real text. But the good part is I used both the technique keyword and vector. And so I was able to answer to the user even when the query is heavily keyword bounded and even when the query is heavily semantic bounded. And thanks to reranking, I do not need to worry to understand which of the two searches is better. I both them in parallel, so I have a possible higher recall, and then simply use a reranker to order the query and know which one sent to my large language model. And I'm using a large language model. I'm using GPT 3.5, but I'm using only 8,000 token as the input context. So I cannot stuff a lot of information. But thanks to Cohere ranking, the very first result is the one who are important. Now, let's go into the code. So this is how I'm configuring kernel memory. So as you can see, it's standard configuration. For file storage, I'm using the disk file storage. It's not production ready, but I don't care about it because the disk storage, it's used only to store pieces of text before it goes into the memory DB. So what is important is that I am going to configure Elasticsearch is an option, so you can even not use Elasticsearch. But if you're using Elasticsearch, you will enable this new capability. So I'm simply using Elasticsearch. I'm giving the base configuration like the address of my local server. But then the most important part is where I'm configuring the user search pipeline. This is the heart of my extension. So instead of using a standard kernel memory pipeline, I'm going to configure a more advanced pipeline. And I can configure more than one pipeline in the system, giving it a name. So in this example, I'm configuring only one pipeline with the default name, but I can configure more than one. So I can choose which pipeline to use. So the first lines are standard registration of all the part of my pipeline inside my services, inside dependency injection. So I'm going to use a Cohere ranker. I'm going to use a standard vector search query handler, and it's the handler of the query that performs standard vector search. I'm adding a keyword search query handler. It's the one that performs a keyword search. And finally, I'm registering the standard RAG query executor, and it's the last part. It's the part that takes the possible memory record from the system and pass to a large language model to have a question. So the standard vector search query handler and the standard RAG query executor are basically the same code that runs inside kernel memory. It's the base pipeline. Now I'm adding a Cohere ranker and a keyword search query handler. And then when you create and configure the pipeline, you can use the add kernel memory user question pipeline. And in the config, you are specifying in the correct order all the handlers. So the first handler is a standard vector search. Then if I'm using Elasticsearch, I know that my Elasticsearch memory DB supports also the keyword search. So I'm adding the keyword search query handler, and then I'm configuring the latest step of the user question pipeline, the standard RAG query executor. And finally, I set reranker, Cohere reranker. So when I configure everything, I have a more complex pipeline that can solve my question. Now, to use my advanced pipeline, you just need to resolve the pipeline factory, user question pipeline factory, and then you can use the create method to create. In this kind of example, I didn't pass any string arguments, so I'm creating the default pipeline, but you can configure more pipeline with different technique, with different handler to solve the user question in a different way with different strategies. As I told you before, this is the very basic RAG pipeline in which I use vector search plus keyword search, then rerank everything, and finally using the large language model to answer. The rest of the code is almost the same. Another important aspect is how can you perform the query? Well, you can simply create a user question object with some option, okay? So you can specify some options to the user query. We can look at the option object, but in this first version, you don't have a lot of option, but it's prepared for future use. And then you can simply use the question pipeline and use the execute query async. And the important thing is, since all the large language model we are using have the streaming capability, so instead of waiting for the large language model to complete all the answer, we can get the answer as soon as it arrives. So we have an IOSync enumerable, and so we can do a wait for each, and so we can look in all the result, and if the step type is the answer part, is a piece of the answer. So this is a part that is still in beta, so you don't have anything else apart from the answer part. But this is important because we can show the answer to the user as soon as the answer is generated by the large language model. And finally, in the following section, it's simple code because I'm gonna execute the check against the inner results to give you the statistic. So to give you the idea of how many positive are returned by the keyword search, how many positive are returned by the vector search, and where are the positive when we do re-ranking. I don't want to go too deep into the code because the code is open. You can check the solution. I only want to give you the key part. So for performing a keyword search, my MemoryDB, my implementation of Elasticsearch for kernel memory, implements another interface defined by my kernel memory extension that is called iKernel Memory Extension MemoryDB. Is the set of functionalities I'm expecting from a MemoryDB to work with my extension. And for now, the only method I have is search keyword async. So the ability to search keyword and not vector search. So a question arises, and it's, why do you need to add another interface? Because I can simply say, okay, I want to do a keyword search. I can search in another database or in anything else. So why do you need to get this interface? Well, this interface is needed for database engine like Elasticsearch and MongoDB Atlas that internally works with Lucene, because they can do both vector search and keyword search. So I don't want to waste space and time for indexing my pieces of text inside two databases, vector database and keyword database. I'm using Elasticsearch or MongoDB Atlas, and they can do both searches. So I'm indexing data with the standard MemoryDB interface of kernel memory, but my implementation of Elasticsearch allow the user to specify which payload field you want to index. And since kernel memory used the text payload field to include all the text, I know that I can create an index in Elasticsearch that can serve both vector search and keyword search at the same time or in different time, but I don't need to add anything else. So thanks to this simple interface, I can use the very index pipeline of kernel memory and have the ability to search, to do keyword search without writing any single other line of code. And that thanks to my custom implementation of kernel memory Elastic. The standard vector search handler of the pipeline is basically copied from the kernel memory because it's nothing new. So we have a method that each step of the pipeline need to implement, and it's on handle async. You receive the user question and a cancellation token. So this is the vector search. So it can simply use the get similar list async from MemoryDB, take all the results, and then for each memory record, simply filter out those ones who are less than a certain relevance and use the add memory record source method that simply tells to the user question, hey, this is one set of possible chunk of text that answer the user question, and they are generated from the standard vector search pipeline. And this is the handling of the keyword search query handler, where it simply uses the advanced MemoryDB performing the search keyword async, and then it's the same. So each handler that try to find memory record that satisfy the used question are simply pieces of text that perform a search inside some database and generate some memory record to the kernel memory result. So this is something I'm gonna change because this uses the memory record structure of kernel memory. So if you're going to add another search capabilities to search, I don't know, maybe from your SQL database, you can extract data. You need to stuff them inside a memory record. And this is something strange because memory record is a specific structure of kernel memory, but this makes me possible to write less code and go up to speed with this kind of examples. Then there is this memory record equality comparer, whose purpose is filter out duplicate result. Because, if you search on the same database, both with keyword and vector search or other technique, maybe different kind of queries, it is normal for some pieces of text to return in multiple query. So we know from memory record structure of kernel memory that a memory record is equal if it says the same document ID, the same file ID, and the same partition number. So this is a simple equality comparer that allow me to deduplicate for reranking. Then I introduce a new interface called reranker that every re-ranking algorithm should implement. And this is the Cohere ranking that uses Cohere API to ask to a remote server using the command R model. This is the model of Cohere to re-rank result. As you can see, it's very simple because it will create a series of memory record. So it's from all the possible candidate searches, so keyword search, vector search, it select many, so it select everything. It distinct, so I can remove the duplicate. I'm creating the list of documents, and I'm simply using a call to Cohere to re-rank the results. And so the Cohere client can re-rank the results and giving to me the list of documents with a score. So I can say I can return from all result. I'm gonna select the index from the old citation, so I can easily give back to the caller all the possible memory record extract from the various technique reordered by re-ranking results. And to call Cohere ranking, it's really simple. I've taken the official documentation and taken a JSON request and a JSON answer from the official documentation of Cohere. And I've used Claude. Thanks to Big Agi, I pass the JSON and tell Claude, hey, please generate me a series of object, C# object, with the attribute of system text JSON that are able to deserialize this JSON. This is a tremendous, a really powerful usage of a large language model. I'm giving them the JSON example, and it generates me all the code I need to call the API. So I didn't need to write almost anything. I simply call an HTTP client in C#, and I'm simply creating the request. I'm adding the API key as the header, and I take the result. All of this code was generated by Claude large language model. And this is how you as a developer can be more productive with the large language model. I only did some minor adjustment, and I was able to use Cohere rank in my example. And we are at the end of the journey. This is the last piece of the puzzle, is the standard RAG query executor. Is the pieces of text that actually perform the G part, the A and G part of the RAG query. And this is taken from the standard code of kernel memory. It's not anything different. I've personalized to work with my advanced pipeline. So the first line is the line 46, where he asks from the user question, get memory ordered. This kind of method is really special because it checks if the records are already ordered. If the first time you call it, it calls rerank, and rerank is not doing anything fancy. If you have no result, you return an empty array. If you have only one source, you can return the same source because, if you only do keyword search or vector search, there's no need for re-ranking. If the re-ranker is null, you throw exception. And if you reach here, it means that you have more than one technique. So I have maybe vector and keyword, like in the previous example. So I simply call the configure re-ranker to re-rank everything. So nothing fancy. If we don't have memory record, I don't return anything. And then I create the fact as a string builder. This is code I've copied from the standard kernel memory, but this is standard RAG code. So I'm checking some information like the maximum number of token I want to use for my large language model request and how many tokens are available. So I'm starting creating a list of all the memory record I'm using. And from all the memory record reordered by re-ranker, I'm starting telling I've taken one more fact. I get a partition text. I count the token of the pieces of text I've returned, And if the size is greater than the maximum number of the token I want to use, I want to pass to the large language model, because as I told you, we can have GPT-4 Turbo with 128K thousand of token. I don't want to use all the token because it's going to cost me money. So I'm giving the maximum number of token I want. So this kind of code is cycling in all the possible memory record in the results, and it's gonna stuff just the right amount of text inside the memory, inside the prompt of the large language model. And if you arrive here, you can increment the number of facts you are using. So you create a fact, and it's a special form of text in which the kernel memory used file in a partition text. But this is just prompt engineering. You can find a lot of RAG example in which you can maybe configure this kind of input for your user and for your specific use cases, and maybe generally speaking, based on the large language model you're using. And then you just append the fact to the string builder, and finally, there's nothing fancy. You can generate answer async and return all of the text while the large language model is gonna generate everything. And in generate answer async, it's really simple. So you have the answer prompt. You start with the standard answer prompt configured in kernel memory. You replace facts with the facts with all the results of your query. And then you replace the input with the question. You replace the not found. Well, this is code taken from kernel memory code. It's the standard way in which you are using a large language model prompt to tell the large language model, hey, I'm giving you a user question and a list of facts, and you're going to answer only using the fact you have in the prompt. This is called grounding, and it's used to remove hallucination. And this basically concludes the piece of the puzzle. So to give a recap, my extension allows to first define an interface that you can implement in your MemoryDB to do keyword search, and I've implemented in my Elasticsearch driver. Then I've added an extension to configure a user question pipeline, as you can see in this code, in which I can simply add a series of handlers that will be called sequentially. Some handler perform query, and the final handler usually is the standard RAG query executor that perform the query to a large language model. I've added the ability of ranking, and this is the main point of the whole example. The ability to search in various techniques and simply say, hey, I have a reranker that will have the really important purpose of taking all the possible solution and bringing to the top the most important one. And the rest, it's very, very simple. It's the same code of kernel memory. So in this simple example, I've used the standard indexer pipeline of kernel memory. I didn't configure anything else in the index part. I've simple give you the ability to do keyword search in parallel to vector search. Then you can re-rank the results. So depending on the question you can have the best of both worlds. Some user query are best answered by keyword search. Some of the user query are best answered from vector search. You can maximize the recall to load a large amount of memory record, because you know that thanks to re-ranking function, you will bring to the top the most important relevant to the user query. And so this tremendously improve the amount of good question, good answer you can give to the user. And it's really, really a game changer. And then with this basic structure, you can customize and put the more search handler you want. You can do as many different search techniques you want, because you will always have your re-ranker that will re-rank, will reorder the result to be sure that you can pass to a large language model a small context with the most relevant memory record results. All this is already usable using some Nugget package I've published. You have the kernel memory Elasticsearch, that is a custom implementation of iMemoryDB for Elasticsearch that also implement the ability to search with keyword. You have the Alcamfer kernel memory extension, that is the base code you saw all the handler you have. And finally, the kernel memory extension interfaces that contains only the interface to make the first two dialogate. All the code is clearly open source. You can find in GitHub in my account. There is the kernel memory extension that contains all the code we saw today. And there's also the kernel memory Elasticsearch that contains the implementation of an Elasticsearch memory DB for kernel memory. And a disclaimer, there is already a kernel memory Elasticsearch driver written by another author. I rewrite my own just because I needed to have my version to implement both vector and search capabilities. So if you already use the old Elasticsearch driver, feel free to ask to the author to implement this interface, my extension interface, if you want to do also keyword search, or feel free to use my kernel memory Elasticsearch driver. All of this code was not still in production, but was written to go in production sooner. So feel free to give me all the idea, suggestion, and bug you can find, and I'll try to keep this code up to date as possible. And surely I'm going to do some fixes or improvement when we will go in production with this code. I hope you like this video, and I hope with this extension you can use kernel memory in a much more advanced way. Kernel memory is an amazing library. It gives you the possibility to create a RAG pipeline with very few lines of code. And I'm hoping with my extension to give you the ability to cover more advanced scenario, always with a very minimum amount of code. So you don't need to worry of the nitty-gritty detail of a RAG pipeline. You just put pieces together and let all the library and extension kernel memory do the rest. Bye-bye and see you on the next video.